So we've talked a little bit about this concept of substrate cycle, and I'm going to revisit that and then talk about a new term that I don't think we've spent too much time talking about, and that's flux. So let's first define what flux is, since that's a new term. So flux is really the flow through a pathway. And as we're going to see, we're going to understand flux as a difference between the rates of forward and reverse reactions. Okay, so fundamentally, I just want you to think about flux as flow through a pathway, but we're going to map on another piece to think about flux in just a minute after we revisit what it means to be a substrate cycle. So generically, let's just imagine that we take substance A, okay, and we convert it into substance B. Okay, and we can think about going in that direction as being the forward direction, and so we can have a rate then for that forward reaction. Because this is a substrate cycle, we also have the ability to then reconvert B back into A, and we're going to say that that's the reverse process, and we're going to have a rate for that reverse process. So generically, the interconversion of A to B and then B back to A is what we call a substrate cycle. And in just a little bit, I'm going to give you examples of 3 substrate cycles that start very specific and then kind of come out to be very general. So here's some general themes for things that I want us to think about when we talk about substrate cycles. Okay, now it's not to say that this is always the case for the forward direction, but let's imagine here that when we think about the thermodynamics of our forward process, the delta G for that forward process is going to be negative. Okay, we're going to say that that is a downhill process, right? Energetically, that goes downhill. I don't need to put extra energy in to have that process happen. Sort of in a big picture, thinking about this from a biochemistry standpoint, things that are catabolic tend to be thermodynamically favorable in this way. They tend to be spontaneous, and these are going to be processes that we see happening during a need state. Okay, so need state are going to be pathways that operate with a net negative delta G. They operate downhill, and that's because catabolic processes break down larger things to give us smaller things plus energy. Okay? Flip side of this is anabolic. So anabolic processes tend to be processes that require energy. So the delta G, so for this reverse process, if we're considering anabolic processes, is going to be positive. That means they are going to require the input of energy. We are going to have to put energy into this system in order to have that anabolic process occur. Again, that's because it is uphill. And in being uphill, okay, that's why we require that input of energy. These are going to be processes that happen when we are in a fed state. So that's kind of putting a whole bunch of pieces of stuff together for stuff that we've talked about already. So I want to map on, before we go through our examples, thinking about what it means, again, to think about flux. So flux is flow through a pathway, and flux also represents the difference between K forward and K reverse. So I'm going to put these guys here down, K reverse and K forward. Okay, and so what I want us to do is think about here what it would mean if we have these rates being equal or one being greater than another. Okay, so we're going to have sort of 3 scenarios to think about here for that. Okay, so let's imagine that K reverse is equal to K forward. So K reverse being equal to K forward. Okay? We would define flux for this system as being 0. So flux for this system is going to be 0. There is no net flow in or out. We're not accumulating more A or more B. Okay? So again, if we think about this as water flowing and showing sort of the conversion of A to B or B back to A. If A to B happens at the same rate as B to A, there's no net accumulation of either A or B. And so we say flux through this metabolic pathway or this substrate cycle or this system is going to be 0. Okay? Let's take another situation here. Let's imagine that the K for the reverse process is going to be less than the K for the forward process. Okay, so that means my forward process is faster than my reverse process. So I'm converting A to B faster than B is going back to A. Okay, the net for this process is that we are going to accumulate B, right? If the forward process is faster than the reverse process, then B is going to be accumulating faster than B is going back to A. So the net is the accumulation of B. And if we're talking about this from an overall system, we are going to be in a state of catabolic flux, okay? If we're assuming that A going to B is a catabolic process. Let's look at the last situation here. If K reverse is going to be greater than K forward, that must mean our anabolic half of our substrate cycle is operating in a greater rate than our catabolic process. In that case, we are going to accumulate A. Okay, so we're going to introduce 3 different sort of substrate systems. Okay, and I'm going to just kind of copy this so I can have it on sort of a blank slide on the next slide so that I can sort of build on what we think about with this. So I'm going to copy this. Go to the next slide. And we're going to talk about 3 different examples of A and B that identify different kinds of substrate cycles. All right. I think this is a word that I didn't need there. All right, so let's talk about different identities of A and B. Okay, so we're going to make a little chart here to talk about different identities of A and B. Okay, we're going to talk about what level of substrate cycle we have here. So we're going to call this a level. Okay, and then we're going to talk about the enzyme or pathway that it's part of. And these are all things that we are going to revisit and see again next semester. Okay, so stuff that we're going to sort of build on. So then we're going to have the enzyme or the pathway that's responsible for that. Okay, so let's imagine that A and B have the identities of pyruvate and lactate. Okay, so this substrate cycle operates on what we're going to refer to as an enzyme level. Because the enzyme or pathway that's responsible, it's really the enzyme, okay? And that's lactate dehydrogenase. So depending on which way lactate dehydrogenase is operating is going to determine whether we're converting pyruvate to lactate or lactate back into pyruvate. Okay? And one of the things that we'll highlight that I hope you remember from this learning unit as a whole is when we are converting pyruvate to lactate, we must be in a need system and we need to regenerate NAD+ in order to have glycolysis continue. That's why we have lactate dehydrogenase doing its chemistry. If that doesn't make sense, go back and kind of look at your notes for sort of thinking about glycolysis and then what happens when we are under anaerobic sort of systems. Okay, so let's talk about another option for pyruvate. What if pyruvate is still A, okay, but then we have glucose as our B, okay? Again, 2 pathways that we've sort of learned their names for, we haven't talked about the details for, but interconversion of glucose and pyruvate is really a pathway level of a substrate cycle. Okay, so let's talk about this. If we have, in this case, A going to B, okay, pyruvate going to glucose, keep my colors consistent here. If we have A going to B, okay, pyruvate going to glucose, that's gluconeogenesis. And then B going back to A, well, we learned that as glycolysis. Glucose going to pyruvate is glycolysis. And you might be saying, well, wait a minute, Dr. Brennan, you have this backwards because like Catabolic processes would be doing things like breaking down glucose into smaller molecules. So we talked about A going to B as being catabolic processes. And so I want to make sure to put this in your brain now. Yes, A going to B is going to be sort of need state pathways. Okay? So a need state pathway is gluconeogenesis. And this is a little bit weird to think about, but glycolysis is a fed state pathway. What? Like we talked about, we break down glucose for energy. How is that a fed state pathway? Big picture. Remember, we cannot have opposing pathways for fed state and need state operating at the same time. So hopefully it makes sense to you that gluconeogenesis has to be a need state pathway. When we are low in our blood sugar and we need to make glucose from non-carbohydrate precursors, that's a need state system, okay? So gluconeogenesis is need state. Glycolysis can't also be need state. And once we start mapping on and thinking about this, it's like, oh, glycolysis is going to be upregulated when we have excess glucose. That's a fed state, okay? So glycolysis, even though it does make energy, but it is a fed state pathway and it will be regulated as such. Okay, the last one to sort of talk about here is, let's talk about this on a much grander scale. We're going to talk about this as being an atom cycle. Okay, so when we talk about an atom cycle, let's imagine that our A molecule is glucose, okay? And then our B molecules are carbon dioxide, water, and energy, okay? So that is really what we refer to as the carbon cycle. So that atom cycle really is the carbon cycle, okay? And if we think about, again, this A to B version, okay, we know that as fuel metabolism. And then the B to A version, we know that as photosynthesis. We know that as photosynthesis. So one of the things that's different about this substrate cycle is it's not going to be something that we can do, right? We can have lactate dehydrogenase kind of going in either direction. We can do glycolysis and gluconeogenesis. We can do fuel metabolism as a catabolic process, but we cannot sit out in the sun and make our own glucose in that way. So analogy breaks down a little bit here in terms of thinking about this is not something that we have the ability to participate in as an atom cycle, but kind of globally in the world, that is a process that can occur.